Hello students. Uh, it's been more than 10 days. I couldn't engage class for you, and I'm still in isolation. So Murali sir helped me to set up this in my home itself. And let us continue our discussion on current electricity. We are left with one more topic, potentiometer. Meter bridge is done, but now I don't want to go for potentiometer because I want to explain potentiometer with the actual potentiometer apparatus in the lab so that you have better clarity about it. We'll take potentiometer by the end of the after discussing the problems, numerical problems of current electricity. So in this session we are going to take uh, problems on uh, current electricity. As you all know, before we take up the problems, we always list the formulae, right? So current electricity, numerical problems. Uh, you should be having the list of formulae with you. Okay, the same formula we are going to follow in the reference success line series. There are somewhere around 26 formulae given. Out of them, we are going to take the first 23 formulae. The first is about the current, electric current, which is I is equal to dq by dt. Okay, this is the basic definition of electric current, rate of flow of charges, right? This shows how fast the charges are flowing through a given cross section. Okay, quite simple. Dq by dt will give you the instantaneous current. Okay, if you take q by t, that will give you the average current for over a period of time chosen in the conductor, right? Next is Ohm's law. Quite easy. In Ohm's law, V is equal to I R. Okay. So here in the first formula, you have I given by the current. dq is the amount of charge, small amount of charge flowing through a given cross section of the conductor in a small time dt. And the second is Ohm's law, which is V is equal to IR, where V is the TPD or terminal potential difference. In simple, we keep that as voltage also. Voltage across the terminals of the conductor. I is the current through the conductor. R is the resistance offered by the given conductor. Next, the formula is for the resistance of the conductor expressed in terms of its dimensions and resistivity. Okay, which is rho L by A. R is the resistance of the given conductor. Okay, in what shape it has given, that shape itself decides the resistance. Rho is the resistivity of the conductor. Okay, resistivity is independent of the dimension. Okay, whatever the kind of conductor that you take, when you do not change the composition, chemical composition of the conductor, the resistivity remains the same, yeah, until you change the temperature. Once you change the temperature, again resistivity also changes, that we'll get to know. But as long as the temperature is constant, irrespective of the dimension, or I can say shape and size of the conductor, resistivity remains same. Copper at 40 degrees Celsius, resistivity is fixed. Okay, and these values are normally given to you while solving problems. Next is length. L is length of the conductor. A is the area of cross section of the conductor. R is the resistance of the conductor. Okay. Next, it is current density, J, given by sigma E. Okay, J is the current density. You should be aware what is J. Current density, I by A. Okay, current per unit area of cross section. Okay, where J is also equal to I by A. Okay, should keep this in mind. Sigma is the conductivity of the given substance, given material. E is the electric field setup inside it. Okay, this we have discussed in detail while deriving the formula of it. Next is drift velocity. Fifth one, drift velocity is given by Vd is equal to E tau by m. This is the formula for drift velocity, where Vd is the drift velocity of the electrons moving inside the conductor, the velocity with which they drift. Okay, should visualize whatever I taught. E is the charge associated with each electron. Okay, the amount of charge with each electron. This E, capital E, is the electric field set due to the external potential difference that you apply. Due to the battery that you connect, there will be an electric field set inside the conductor. That is what is this E. And tau is the relaxation time. Okay, the time spent by average time spent between two successive collisions, relaxation time. M is the mass of electron, and this is the expression for drift velocity, Vd. Next is mobility of the electrons in a conductor. Mobility mu is given by E tau by m. Okay. Here we define mobility as the drift velocity acquired per unit electric field or per unit external electric field applied in the conductor, right? Vd by E itself is mu, right? So you send E here, you will be left with E tau by m, right? So that is what is mobility. How with see, if you apply less electric field inside the conductor and you are observing more drift velocity acquired by the electron, then we say mobility of the electrons is good inside that conductor. But if you apply more electric field, say you are connecting a very very large battery, but even then you are getting very less Vd, drift velocity is very less, then we can say the mobility of free electrons in that conductor is less. Okay, that is about mobility given by mu. Next is our familiar expression. Okay, not sure how much part is it visible for you. Yeah, let me not write in this part. Okay, seventh formula, current expression, the other expression for current, I is equal to NEAVD, right? I is the current in the conductor, total current in the conductor. N is the electron density, okay, free charge density or electron density, number of electrons per unit volume inside the conductor. That is what is this N. E is charge of the electron. A is the area of conductor of the area of cross section of the conductor. Vd is the drift velocity of electrons. Okay, so this is again an important expression, which is also important in the result of an important derivation. Okay, next from this, yeah, based on necessity you can get plenty of formulae, okay, for J, R and all in using this. Okay, but these are the basic formula you should be familiar with, because see, for current density now I can write J, the basic formula for J is I by A. What is I here? I is NEAVD. A and A cancels, you'll be left with NEVD. Okay, this is one more formula for current density J. Okay, keep that in mind. Next you have an expression for electrical conductivity given by sigma is equal to N E squared tau by m. Okay, the same representation for symbols. N is electron density in the conductor, E is charge associated with each electron, tau is the relaxation time, m is the mass of electron. Sigma gives you the conductivity. Now the reciprocal of conductivity itself is resistivity. So I can write rho is equal to 1 by sigma is equal to reciprocal of this, which is m by n e squared tau. Okay. So this is the expression for electrical resistivity. And then this is an important expression. Here in this expression, the next expression that I am going to take is the one which connects mathematically how the resistivity of certain material, certain conductor varies. Okay. So let me write the expression once. Rho is equal to rho naught of 1 plus alpha into T minus T naught. Okay. Look at this expression. Here rho generally represents the resistivity, right? Even here rho represents resistivity. Here this rho, there is difference between the rho and the rho naught here. Okay. Rho is the resistivity of certain material, any material that you choose, let's say copper, steel, aluminum, iron, gold, silver, etc. Rho is the resistivity of the material at temperature T Kelvin. Okay. You can keep the temperature in degrees Celsius, that doesn't matter, because we are going to consider the difference here, difference of temperatures. Okay. Okay. Rho is the resistivity of the given substance at temperature T Kelvin. Rho naught is the resistivity of the same material at temperature T naught. Okay. Say you know the temperature, you know the resistivity of copper at 20 degrees Celsius, and you are asked to find the resistivity of the same copper at 80 degrees Celsius. So you are given with T 80, T naught 20, rho naught will be given, what is the resistivity at 20 degrees Celsius, and you are asked to find rho. Is it possible to find? Yes, you can calculate it. And one more important factor that is that will help us is this alpha. Alpha is the temperature coefficient of resistivity, and this alpha is unique for each substance chosen. You choose copper, you have different alpha for that. You choose aluminum, you have different value of alpha for that. You take iron, different alpha. Similarly, you take different substances, they will have their own alpha value. Okay. So clear with this? Rho is the resistivity at T degree Celsius or T degree Kelvin, T Kelvin. Okay. Doesn't matter whether you take the temperature in Celsius or Kelvin, because you are going to take the difference of temperature. Okay. But either degree Celsius or Kelvin, not the other way. The Fahrenheit and all are not considered. Okay. So better you keep it in Kelvin itself. So rho is the resistivity at temperature T Kelvin. Rho naught is the resistivity at T naught Kelvin. Alpha is the temperature coefficient of the given material. Okay, a single material. So this gives the mathematical relation how the resistivity changes for a given substance, for a given material with respect to temperature. Okay. And in the same formula, if we do not change the dimensions of the conductor, say you have a conductor of area of cross section 1 millimeter squared and length 2 meters, and you do not change the dimension of the conductor, when that is the situation, when you are not changing L and A, R is simply dependent on rho, right? So when the dimensions are not changed, okay, when the dimensions are not changed, okay, only temperature is changed. You have taken 2 meter copper wire of 1 millimeter squared area, and you have changed the temperature, you have heated it to a higher temperature. Dimensions are not changed. Okay, thermal expansions are all neglected, nothing to worry about it, they matter least for us, but the temperature is changed. area of cross section is not changed, and the length is not changed. That will give us the relation for resistance directly, since the dimensions are not changed. I can write directly, instead of rho, I can write R is equal to R naught of 1 plus T minus T naught. Okay, so this is again an important formula. When the dimensions are normally dimensions are not changed when it comes to changing the temperature, but this is the standard formula, and this is the formula when the dimensions of the or the size and shape of the conductor are not changed. This is how it comes. So this is about few formula. Let us continue. Moving ahead, 12th formula is about electrical power dissipated, or ohmic loss. Okay, when you have a power dissipation, when you have normally that whatever the conductor that we choose, that conductor will have its own resistance, and due to that resistance we can expect the certain amount of heat to be dissipated in the conductor. Okay, so that heat is also called ohmic loss, power dissipation. It is given by P is equal to Vi. Okay, this is the amount of power loss that happens when you have V volts applied across the terminals and high amperes of current flowing through the conductor. This much power loss is expected. Now again, applying Ohm's law here, we can get a few more formulae for the same power loss. I squared R is 1 is equal to V squared by R is the other one. Okay, this is for power loss, or we can also call that as ohmic loss. Next is about combination of resistance. When you have resistors connected in series, the effective resistance given by Rs is simply equal to R1 plus R2 plus R3 plus so on. Okay, n number of resistance we can connect and get the effective resistance. Similarly, when we have n number of resistors connected in parallel, okay, then it is 1 by Rp, where Rp is the effective resistance of the combination. Okay, combination involves n number of resistors connected in parallel for Rp. Rs is the effective resistance of the combination when you have n resistors connected in series. Okay, so 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. Okay, so this is combination of resistors. And similarly, when you have n similar resistors connected, equal resistors connected, then Rs becomes equal to n times R, right, where R is the same resistor connected n times. Okay, or I can say n same resistors of resistance here are connected in series. Okay, same resistors, R ohm, R ohm, R ohm, R. Then Rs becomes simply NR. And for this, when you have n equal resistors connected in parallel, 1 by Rp becomes equal to n by R, or Rp is equal to R by n. Okay, so this is for n equal resistors connected in parallel and in series. Okay. Next is again an important formula, the relation between TPD, terminal potential difference, and the EMF, which is given by V, TPD V is equal to EMF of the cell minus current through the cell or the current through the circuit multiplied by the internal resistance of the cell. Okay, V is equal to E minus IR. V is TPD, terminal potential difference, the actual voltage by the battery. E is the EMF of the cell, okay, which is the maximum ability of the battery, I can say. I is the current through the circuit, because you can expect TPD only when the circuit is closed. When the circuit is closed, there will be flow of current. And I is the current flowing through through the cell. R is the internal resistance of the cell. Okay, we have discussed about this. Every cell will have its own internal resistance. Even the dry cells that we choose will also have their internal resistance, and that internal resistance is small r. Internal resistance of the cell is this. Okay, yeah. Next is when you charge another battery using the source of EMF. Okay, so this is a new one which we have not discussed. The net EMF E becomes equal to TPD minus E, small e. Okay, where this small e is the EMF of the battery which is charged. Okay, see, normally what happens in all the remaining circuits that we have discussed is we connect either a resistor. Normally we connect a resistor, okay, for the study, but here we are connecting a battery itself, a rechargeable battery, and source EMF that we have, which can also be a battery, is E volts. TPD after charging the battery of EMF small e will be V volts, and E is the EMF of the battery which is charged. Okay, the new battery which we have introduced and charged, just like charging a mobile phone. Okay, you charge a battery charge the battery of your mobile phone to the EMF small e using an external battery, a large battery, you can assume, using that large battery like a power bank. Okay, this E is the EMF of that power bank. V is the actual potential difference between the terminals of the power bank. E is the charge EMF of your battery of the mobile phone. Okay, that is how you can visualize and connect them. Okay, this is about next formula. Yeah, and current through the cell, current through an external resistance capital R connected to a cell is given as follows. I is equal to EMF E divided by R plus small r. Okay, this I is the current through an external resistance and the battery. Okay, see, somewhat like this. You have the simplest circuit like this. Okay, this is the resistance capital R, external resistance connected to the circuit, and this is the cell of EMF E and internal resistance small r. Every cell will have its own internal resistance and its own EMF. Okay, when you have such a circuit, then there will be a certain current through the circuit, right? And that current is given by I is equal to E by R plus R, where R is the external resistance of the circuit, small r is the internal resistance of the cell. I is the current through the entire network. You take inside the cell, you take out in the conductor, inside the resistor, whatever the part you consider, I is the current, constant current throughout the circuit. Clear with this? I is the current through the circuit. E is the EMF of the cell, small r is the internal resistance. In some problems, they themselves mention that you can neglect the internal resistance. In that situation, you have to consider the same formula, but you should make small r become small r equal to 0. Okay, so that's about the next formula. And next we have combination of cells. Okay, when we have series combination of cells, effective EMF is given by, okay, ES is the effective EMF of series combination of cells, which is given by E1 plus E2 plus E3 plus on up to n cells, okay, for series combination. The combination looks somewhat like this, right? What if one of the cell has changed its direction? Somewhat like this. See, E1, E2, E3, E4. This is the case when you simply write E1 plus E2 plus E3 plus so on. If this is the situation, the net EMF will be E1 minus E2 plus E3 plus E4 and so on. Okay. The cell which has changed its direction will have a negative sign with the EMF value of it. Okay. Right. So this is for series combination. And the internal resistance for the series combination is also simple. Rs is equal to R1 plus R2 plus R3, so on. Okay. Now for parallel combination of cells, the expression for effective EMF is EP, the effective EMF, by RP. RP is the effective internal resistance of the combination of cells, okay, which is similar to this expression. Okay, when you have n cells connected in series, their internal resistance is going to the effective internal resistance will be given by 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. EP by Rp is equal to E1 by R1 plus E2 by R2 plus E3 by R3, so on. Okay, this is more general equation. Okay, but particularly when it comes to numerical problems of boards, they normally stick with two cells connected in parallel. When that is the situation, you can directly write the expression for EP given by EP is equal to E1 R2 plus E2 R1 divided by R1 plus R2. Okay, you can get back the same expression. Okay, that's not a problem. It's easy, you can work it out. Rp is R1 R2 by R1 plus R2 for two resistors, right? You can put it and obtain this expression. Okay, clear with this? This is for more general equation. N resistors connected in series, n cells connected in parallel. Okay, sorry, n cells connected in parallel. This is for two cells, only two cells connected in parallel. The EMF is EP, E1 R2 plus E2 R1 by R1 plus R2 is the expression. The advantage of this expression is you don't need to calculate Rp to get EP here, right? You directly have EP using the expression values of E1 R2, E2 R1, R1 and R2. These are all directly given. But when you have more than two cells connected in parallel, then you have to find Rp. How do you get Rp? Rp is obtained like this. We get Rp using 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on. Okay, we have to follow this we have to follow this formula first and apply that here when we have more than two cells connected in parallel. If we have only two cells connected in parallel, we can directly come to this formula and get the value of EP. So that is about equivalent resistance, equivalent internal resistance. Okay, even the internal resistance for this only two cells is given by similarly Rp is equal to R1 R2 by R1 plus R2. They have mentioned it as R equivalent. That's also fine. Next is about Kirchhoff law. First Kirchhoff law, the KCL, Kirchhoff's current law, which is given by summation of currents through a node is equal to 0. Okay, remember the rules. Current entering the node are taken as positive, current leaving the nodes are taken as negatives, and hence we add them, and the final value should be final value of final sum of all the currents should be equal to 0 for a particular node chosen in the electrical circuit. Okay, so here I1 is taken as positive, I2, I3, I4 are all taken as negative. That's not mandatory, again, it's relative. You can choose in a different way. You can choose these three as positive and this as negative. Okay, in some problems themselves will give certain current as positive, so which means that the currents which are in the same direction as of that will be acting as positive, and which is in the opposite direction of that will be acting as negative. Okay, see here, if they mention I2 is positive, I3, I4 automatically becomes positive because they're in the same direction of I2, and I1 automatically becomes negative. Okay, if they give particularly one of the current as positive, then all the currents similar to that will be positive, the current which is opposite to that will be negative. And this is the formula. Summation of all the currents is equal to 0. Next is about Kirchhoff loop rule, or Kirchhoff's second law, or Kirchhoff's voltage law. The expression is, yeah, summation of EMFs. Okay, summation of EMFs is equal to summation of current and the resistances in the loop. Again, you have to follow the rules. Okay, we have discussed about the basic rules of Kirchhoff's second law, voltage law. When should be the EMF to be taken as positive, or when should we consider the EMF as negative, that should be kept in mind. Okay, I hope you remember all of that. If you approach positive terminal of the cell first, okay, then it should be, the EMF should be considered negative. If you approach negative terminal of the cell first while traversing, then EMF should be considered as positive. And when it comes to product of current and resistances, if we sorry, if we have the value of current, if you have the direction of current in the same direction of the traversal, then they should be considered plus IR. If we have the current flowing in the opposite direction of traversal, then we should consider that as minus IR. Okay, yeah, we'll have more clarity on it once we solve few problems based on this. Okay, yeah, next is about a balanced condition of Wheatstone's network. Okay, you should remember all the circuit diagram of the Wheatstone's network. P, okay, I hope you remember that. P, Q, R, S, and you'll have a galvanometer here, you'll have a battery here. Okay, when do we say the circuit is balanced? When the Wheatstone's network is balanced, when the current through the galvanometer is 0. Okay, when Ig is 0, we say the circuit is balanced. And when Ig becomes equal to 0 in the circuit, the connection or the relation between PQRS, okay, when the circuit gets balanced, then the relation between PQ and RS becomes P by Q is equal to R by S. Even if you change galvanometer and the battery from their places, you replace them, you put battery here, galvanometer here, that will not change the balanced condition for this. Okay, this is balanced condition of Wheatstone's network. Again, an important formula. Next is about the same Wheatstone's network applied practically into a meter bridge, and the expression for unknown resistance P is given by Q L by 1 minus L. Okay, again, why this 1 minus L? Because we choose 1 meter length wire, and L is the length at which the the meter bridge gets balanced. So this is the expression for this P is unknown resistance connected. Remember meter bridge was like this, right? here we connected an unknown resistance P. Don't know what is the resistance here. Here we connect a standard resistance. The standard resistance that we connect here is named as Q. And from this point, we'll take a galvanometer and the jacky slides on the wire at certain length L. From this end, we see that the galvanometer reads zero deflection, shows zero deflection. When that is the situation, we say the circuit is balanced. Okay, and anyhow we'll be knowing the value of Q. What we need or what we are interested to find is the value of P, and that P is equal to QL by 1 minus L. L is obtained through practical observation after getting to know the point where the circuit gets balanced. Clear? Okay, so these are the formula of third chapter, current electricity, which are very important for our further discussion. And from the next session we'll be starting with the problems. The problems are simple here, don't need to bother one, but the main part from your side, I expect is you memorize this formula. Okay, not completely like rote memorization is what I expect. You just go through them, you be familiar with the formula, but as we solve more and more problems, you'll memorize the formula by yourself. Okay, so that is one important way, effective way of memorizing the formula. Okay, not by rote memory, instead by solving more and more problems on that formula, you can easily memorize that formula, and you'll get handy with the calculations also. Okay, so from the next session you be ready with the calculator and all. We'll solve few problems and on current electricity. Thank you.